In grade 1, we learned that 3 plus 4 was always equal to 7. That's because in grade 1, we were adding scalars together. Although we didn't call it adding scalars, that's what we were doing. There was no direction associated with the 3 or the 4. It was just a number, the 3 and the 4, and we added them together, and we always got 7. Then we went in grade 5 or grade 6 and added 3 plus 4. Sometimes in grade 6, 3 plus 4 was equal to 7. Sometimes in grade 6, 3 plus 4 was equal to 1 if the 4 was the other direction, was a minus. And sometimes 3 plus 4 was equal to negative 1 if the 3 was a minus. So in other words, in grade 6, we learned to add negative 3 plus 4 is equal to 1, or 3 plus negative 4 was equal to minus 1. In grade 6, we were adding vectors together. We learned to add not 3 plus 4, but we learned to add 3 to the west plus 4 to the east, or 3 to the north plus 4 to the south. We learned to add vectors together in one dimension, east-west or north-south. Now here we are in grade 11, taking physics 20, and we're learning to add 3 plus 4 together now here, and we see that 3 plus 4, well, it could still be equal to 7 if we're adding scalars, or it could still be equal to plus 1 or minus 1 if we're adding vectors in one dimension. But 3 plus 4 now could also be equal to 5. The reason being, now we're learning to add 3 to the north plus 4 to the east. We're learning to add vectors in 2 dimensions. When we're adding these vectors in 2 dimensions to solve a problem like this, what we have to do is remember first to draw a vector diagram. Remember the goal? You guys remember the goal from yesterday? You always want to get what? A right-angled triangle. You always want to get a right-angled triangle that is a vector diagram. So we have to draw that vector diagram and hopefully get a right-angled triangle from that. To do that, you've got to remember what a vector is, or how to represent a vector. It's a line segment with an arrow on the end of it. So if I have a vector that is 3 to the east, then I'm going to draw it like this, 3 to the east. If I have a vector that's 4 to the south, then I'm going to draw it like this, a little bit longer than my 3 to the east, put an arrow on the end of it showing it's to the south. If I want to add 3 to the east and 4 to the south, then I need to connect these vectors into what we call a vector diagram. Remember the rule for vectors in a vector diagram? What order do we draw them in? Can I just do whatever order I want? So let's say 3 like this plus 4 like this. Does that work? That doesn't work, no. Neither does this. 4 like this, 3 like this. That doesn't work either. What's the rule? You got to draw it head to tail. This is the head of a vector. This is the tail of a vector. Now I do have 2 options here. My 2 options are this. The head of the 3 vector to the tail of the 4 vector, or I could draw it the head of the 4 vector to the tail of the 3 vector. Both of those are okay, right? Now, the resultant vector, which is really the 5, it's the sum of all the vectors. The resultant vector is the one that's drawn from start to finish. And that's the one that I either draw as a dotted line or another color, just so it's a little bit easier to distinguish my resultant or the sum of my vectors from all my components. I'm going to draw right here from start to finish. Label it R. Draw right here from start to finish. Label it R. Notice those 2 resultant vectors look pretty much the same. Should they be? Yeah. 3 plus 4 is equal to whatever, whether we're adding 3 plus 4 or 4 plus 3. It doesn't matter which one we add first. Okay, we should get the same sum. Remember, when you're adding these vectors together, 3 plus 4 is equal to 5. Where does the 5 come from? The hypotenuse, right? You use the Pythagorean theorem to do the hypotenuse. A squared plus B squared equals C squared. Or C is equal to the square root of A squared plus B squared. Or in other words, R is equal to the square root of 3 squared plus 4 squared. And when you do that, you end up getting 5. Make sense? We did a couple questions like that yesterday. Okay, the trick is, remember the goal. get a right angle vector diagram, right angle triangle vector diagram. But remember all the little rules, like draw your vectors head to tail, except your resultant vector, which is what you're looking for here, which is what you're going to draw from start to finish. Now, what if we get one like I left you with yesterday, where we have 3 or 4 or even 5 vectors that we have to add together? What if we have one that looks like this? Let's make that 4. Let's make this 6. Let's make this 2. Let's make this 2. And let's make this 8 this way. That's like what, 1, 2, 3, 4, 5 different vectors that we have to add together? The resultant vector goes from start. By the way, are those all drawn okay? Sure they are. They're all drawn head to tail, head to tail, head to tail, head to tail, head to tail. The resultant vector is drawn from start to finish. How do I find that resultant vector? Remember, goal, get a right angle triangle vector diagram. And to do that, I've got to break it into components, x and y. Remember what x and y is? Okay, this is x. This is y. How much of that first vector, that 4 meters, is on the x-axis? How much of that 4 meters is this way? 4 meters, all of it is. That whole 4 meters or 4 whatever units it is on the x-axis. Good. How much of it's on the y-axis? Rachel S. How much of that 4 meters is up and down? None. None of it, right? So we're going to say the y component of that is 0. How about the 6? How much of that is on the x-axis? 0. Good. How much of it's on the y-axis? -6. Good. Who said negative? Okay, good. -6 because it's going downwards. Not just 6, but -6 because it's going downwards. Good. Next one, this 2 meters. How much of that 2 meters, Josh, how much of that 2 meters is on the x-axis? 2 meters. We're going to make it negative, though, because it's going to the left. Maddie, how much of it's on the y-axis? Good. Because it's all on the x-axis, right? How much of that 2 meters is on the x-axis? Patrick? Good. How much of it's on the y-axis? 2 meters. +2 because it's upwards, right? And finally, we got one more. That's this 8 meters right here. How much of that one's on the x-axis? How much of that one's on the x-axis, Ben? 8. Good. How much of it's on the y-axis, Ben? Good. So now we add these together. 4 plus -2 plus 8 gives me 10. 0 plus -6 plus 2 gives me -4. What do I do with those two numbers? Redraw it. I get 10 to the east. How did I know that was the east as opposed to west or south or north? It's positive, and it's the x component, right? So it's to the east. This is 4 to the south, and the resultant vector is right here. Isn't that the same resultant vector I drew before? It should be. If it's not, you've made a mistake somewhere. How do you find that value of r? Yeah. A squared plus b squared is equal to c squared. So r is the square root of 10 squared plus 4 squared. C is the square root of a squared plus b squared. So that's going to be the square root of 116. And I think it's just going to be 10.1 or something like that, 10.2? 10.7? Okay. Thank you. 10.7 meters or whatever our number is there. Good? Now, remember what we said yesterday? We're not really done, but we haven't done anything else with it yet. What else do we technically need for this? The angle, the direction. This is a vector, right? Vectors have direction associated with it. We just haven't learned to find that angle yet. We'll deal with that. We'll deal with that in just a few minutes. I left you with 2 questions for homework, 2 board questions for homework. Sorry, I guess it was 3. 3 board questions for homework. I'm going to do all 3 of those now. The first question said we had 100 meters to the east, 200 meters to the south, 300 meters to the west. 100 meters to the east. We had 200 meters to the south. And we had 300 meters to the west. Is that drawn okay? Could I have changed the order that I draw those in? Sure, it doesn't matter what order you draw them in, as long as you draw them, what's the three-word phrase? As long as you draw them head to tail. As long as I draw them head to tail, it doesn't matter what order I do them in. Now my resultant vector is going to go from start to finish. We'll label that R. Okay, I don't know a way to find that value of resultant vector right away, so what I'm going to do is break it into my x components and my y components. What's the x component of the first one? Francis, what's the x component of the first one there? Good. What's the y component? Good. What's the x component of the second one, Georgia? The x component of it? 0. What's the y component of it? Negative 200. Good. What's the x component of the third one? Ben, what's the x component of the third one there? Good. Negative 300 because it's to the left, and the y component is 0. Add these up. 100 plus negative 300 gives me negative 200. Okay, 0 plus negative 200 gives me negative 200. Oh, this works out perfect. Negative 200 this way gives me a resultant vector of, well, we're going to say it's the square root of 200 squared plus 200 squared. Square root of 3200. Does anybody have a number for that? Thank you. 282 meters. Now, technically, there should be an angle there, which we haven't learned to find it yet, but if you remember a little bit of trigonometry, this one's actually a pretty easy one. Anybody want to take a stab at what that angle is? Don't worry if you don't get this. It's 45 degrees. How'd you know it was 45?
Because 200 and 200 are the same.
Yeah.
So.
Yeah, as long as they're the same, the x and the y are the same, it's got to be 45, right? If they're not the same, then all bets are off. You're going to have to do the calculation, which we'll learn in just a few minutes. So 282 is our answer for the magnitude of the resultant. We just, in a few minutes, are going to have to learn to find the direction as well. Okay, number 2. 2, we have 50 meters to the south, 20 meters to the west, 80 meters to the north, and 30 meters to the east. 50 south, we have 20 west, we have 80 north, and we have 30 east. So our resultant vector will go here. I don't know, a quick way to find that. So what I'm going to do is, well, same thing as I did for the last question, x and y. How much of that 50 is x? Christine, how much of that 50 is x? Not 0. Oh, sorry, no, you're right. Sorry, I was looking at the wrong one. You're right. How much of that 50 is x? It is 0. How much is y? You were about to say that when I... Good. Good. 0 and negative 50. Good? Debbie? Yeah. How much of the 20 is... How much of the 20 is x? It's negative 20 because it's to the left. How much of the 20 is y? 0. How much of the 80 is x, Josh? 0. How much is y? 80. Good. And Rachel, how much of the 30 is x? 30. How much is y? 0. Good. So we add these up, we get 10. And we add these up, we get 30. We're going to say 10 and 30. I didn't draw this quite to the same scale, but you can see my resultant vectors in the same direction, right? I can find this. R is equal to the square root of 10 squared plus 30 squared. It's the square root of 1,000, which is 10, 30, so 30 31, 32?
31.6.
31.6. Thank you. Whoops, not degrees. 31.6 meters. By rights, we should find that angle right here. The angle, by the way, the angle that we always find in just a moment when we go to find it will always be measured at the start of your diagram. Does that make sense? Like you don't want to ever label it up here because that's at the end of it. If somebody says, where do you live? You're not going to give directions from your house. You're going to give directions from the start, from their house, to get to your house, right? Good? Okay, we had one more. This one was 10 meters to the east. We had 20 meters to the south. We had 20 meters to the west. We had 40 meters to the north. And the resultant vector would go here, although we can't really find it there, so we got to do our thing. Who haven't I called on yet? There's the bus. There's like 3 or 4 guys around you throwing you under the bus. Okay, very good. What is it? What's the x component? 10, good. And what's the y component? Good. Anybody else I haven't called on? I think I've got everybody, didn't I? Okay, I guess we start again. Kevin, I haven't called on you, have I? No? 0, negative 20, good. X component here?
The x.
Yeah.
That.
For this one?
Yeah.
Negative 20, and the y component is? Good. And for the last one here, the 40 meters, x component is, let's go Rachel S. I know I called on you, but I think I'm going second time through. What is it? Good. And the y component is? Good. Add these up, we get negative 10. Add these up, we get positive 20. Let's say 10 to the left and 20 up. By the way, could you have drawn it this way? 20 up and then 10 this way? Would that be okay? Sure. Both are correct. Okay, in both cases, you end up getting the same value of the resultant vector. It's square root of 20 squared plus 10 squared. The square root of 500, which I think was 20, is it 22? 22.4. 22.4? Now, the one difference will be when we go to find the angle here will be different than the angle here. But that's not a big deal. Okay, it's just 2 different frames of reference. It's like saying, where is your teacher right now? Your teacher is 2 meters from the front of the room, or you could say your teacher is 6 meters from the back of the room. 2 different numbers, right? But both are correct. It's just 2 different frames of reference. And that's all we've got there. 2 different angles, but there'll be 2 different frames of reference. So when we calculate those angles, you'll see what we mean by that. Right?